Welcome everyone to our last lesson on the energy series. Today we will investigate the conservation of mechanical energy. We will be doing a lot of calculations during this lesson, so make sure that you have a paper, a pen and your calculator ready. We will join Rosie and Chad to tell us about the conservation of mechanical energy.
We know that a quick way to remember potential energy is to think of position. And to remember kinetic energy, we think of motion. Can you still remember the equation we use to calculate potential energy?
Isn't it potential energy equals mass multiplied by gravitational acceleration multiplied by height? The unit is the joule.
That's right, Chad. The equation is potential energy equals mass times gravitational acceleration times height. The unit we use for potential energy is joule. Let's try an example. Calculate the potential energy of a 10-kilogram mass at 100 meters above the surface of the Earth and at the bottom of a vertical mine shaft 1,000 meters deep. Let's start by calculating the potential energy of a 10-kilogram mass 100 meters above the surface of the Earth. Using mass times gravitational acceleration times height, we multiply 10 by 9,8 by 100. This is 9,800 joule, which is the same as 9,8 kilojoule. Next, we need to find the potential energy of the 10-kilogram mass 1,000 meters below the surface of the Earth in a mine shaft. Remember, we are trying to determine how much energy the mass possesses because of its position at the bottom of this mine shaft. Why don't you try this one?
Nice clue, thanks. So, because we are looking for energy due to position, we'll use the formula for potential energy. Mass times gravitational acceleration times height. By substituting, we get 10 times 9,8 times... Oh, how will we indicate that the mass is underground?
Excellent question. Well, the mass in the mine shaft is 1,000 meters below the surface, the opposite direction to a mass above the Earth. So we would use negative 1,000 meters. At the Earth's surface, the potential energy is 0 joule. Above the Earth's surface, it is a positive value, and below the Earth's surface, the potential is negative. The negative value tells us that energy is required to get the mass back to the surface.
That makes sense. Okay, so substituting in negative 1,000, then the potential energy is negative 98,000 joule.
Great. Looks like you've got a handle on potential energy. Now, on the other hand, kinetic energy is the energy an object has because of its motion. Any object that moves will have kinetic energy. The amount of kinetic energy an object has can be found by using the formula kinetic energy equals half the mass times velocity squared. Kinetic energy is measured in joule, mass in kilograms, and velocity in meters per second. We've done some of these before, so let's try a calculation to find the kinetic energy of an object together. A cricket ball of 145 grams is thrown so that it reaches a speed of 25 meters per second. Calculate the kinetic energy of the ball. It's always a good idea to begin by writing down the information given. Here we see that the mass is 145 grams. But remember, we need the mass in kilograms. So I'm going to record the mass given as 0,145 kilograms. The velocity is given as 25 meters per second, and we need to find the kinetic energy. Now, let's substitute these figures into the kinetic energy equation. Using the figures for mass and velocity, we calculate half times 0,145 times 25 squared. This gives an answer of 45,31 joule. We've discussed and calculated the two forms of mechanical energy, potential and kinetic energy. I think it's time to look at the conservation of mechanical energy. The principle of the conservation of energy states that the total energy of a system remains constant. Energy cannot be created or destroyed, but may be converted from one form to another. Do you think this statement is true?
I'm not sure. I do sometimes feel that I run out of energy and feel too tired to run anymore, but I feel better after resting and eating something.
Well, why don't we look at an example that illustrates the idea of the conservation of energy? Imagine we drop a ball with a mass of 0.5 kilograms from a height of 4.9 meters. The velocity of the ball is 9.8 meters per second when it hits the ground. The total initial mechanical energy of the ball is equal to the initial potential energy of the ball plus the initial kinetic energy of the ball. We substitute values into the equation. Notice the initial velocity is 0 and the answer is 24.01 joule. Next, we calculate the final total mechanical energy of the ball. Here, the velocity of the ball is 9.8 meters per second, and the height above the ground is 0 meters. And the answer is also 24.01 joule. What conclusion can you make from these calculations? Yes, we can say that mechanical energy is conserved because the mechanical energy at the start is equal to the mechanical energy at the end. Mechanical energy is conserved when the effects of friction are negligible. We call this a closed system. When there is friction, we have an open system.
Thank you, Rosie. We now have a good idea about the conservation of mechanical energy. Remember, in grade 10, we deal only with closed systems. A closed system is also known as an isolated system. This system is where there is no external force, such as friction or air resistance, only the force of gravity that acts on the object. A closed system obeys the law of conservation of energy. Rosie showed us an example of an object that was dropped vertically. Another example of the conservation of mechanical energy is the movement of a pendulum bob. This time, Keke will tell us about the pendulum. Before we join her, please take note that the gravitational acceleration is 9.8 meters per second squared, as on the data sheet, but lots of textbooks use the value as a rounded off value of 10 meters per second squared to make the calculation easier, as Keke did. Remember to use the data sheet value in your calculations.
The pendulum is a simple piece of apparatus that has been used in many different situations, from clocks to toys to sporting equipment. In each of these, the pendulum is an ideal piece of apparatus to show how energy is transferred. Have a closer look at how a pendulum works.
The mass piece, called the bob, is lifted to one side. The bob gains gravitational potential energy since it is a certain height above its reference point. At the highest point, the bob only has gravitational potential energy and no kinetic energy. When the bob is released, it begins to move and it gains kinetic energy.
Can you see that there is a transfer of energy from potential to kinetic as the bob falls to its lowest point? Now, as the pendulum continues to swing upwards, it gains potential energy but loses kinetic energy until it reaches its maximum height. Here the bob stops, changes direction and gravitational potential energy. It's converted to kinetic energy again. In fact, if there were no frictional forces acting on this pendulum system, it would swing to and fro, transferring energy from gravitational potential to kinetic energy forever. Now, let's have a more careful look at the pendulum to see how the gravitational potential energy changes while the bob swings. When the pendulum is at rest, the bob hangs straight down. At this point, the potential energy of the bob is a minimum. To set the pendulum in motion, the bob is displaced to the side and lifted a little higher than its rest position. Work is done on the bob to lift it to this new height, and so the bob gains gravitational potential energy. Can you find out how much work is done when the pendulum of mass 50 grams is displaced through a height of 40 millimeters? Remember, the work done is equal to the gravitational potential energy gained. We can use the equation EP equals mgh. Before we substitute in the values, let's make sure we have the correct units. The SI unit of mass is kilograms, so we must convert from grams to kilograms. So 50 grams is equal to 0,05 kilograms by 10 meters per second squared. And height has to be in meters, so 40 millimeters is equal to 0,04 meters. Using my calculator, I find that the pendulous bob is increased by 0,02 joule due to the work done in lifting it against a gravitational field. We can say the bob has 0,02 joules more stored energy at the top of the swing compared to the bottom. When the bob is released, the stored energy is converted into kinetic energy. Notice the gravitational potential energy of the bob at its highest point is equal to the kinetic energy of the bob at the lowest point. Well, the gravitational potential energy gained when the bob was lifted was converted into kinetic energy. So at the lowest point of the swing, the bob has 0,02 joule of kinetic energy. This example shows how work, gravitational potential energy, and kinetic energy are related.
Thank you, Keke. We now have enough information so that we can calculate the velocity at the lowest point of the path of the pendulum by making use of the formula for the conservation of mechanical energy. The total mechanical energy at point B, which is the bottom of the pendulum, is equal to total mechanical energy at point A, which is the highest point of the pendulum. So the total mechanical energy at B is the potential energy at B plus the kinetic energy at B. This is equal to the total mechanical energy at A, which is the sum of the gravitational potential energy at A plus the kinetic energy at A. We substitute in the formulae that we know for gravitational potential energy and kinetic energy, which leaves us this expression. We will substitute the values that Keke used, except we will use the gravitational acceleration as 9,8 meters per second squared. The mass of the bob is 50 grams. This converts to a mass of 0,05 kilogram. The height above the ground is 40 millimeter. The height needs to be in meters, so when we divide it by 1,000, we get 0,04 meter. At point A, the velocity of the bob is 0. At the lowest point B, the gravitational potential energy is 0, since the height above the reference point is 0. Let's first calculate the total mechanical energy at point B. Since point B is the lowest point, the height is 0 and the gravitational potential energy at point B is 0. The kinetic energy component is 0,025 multiplied by the velocity squared. Now we can calculate the total mechanical energy at point A. At point A, the velocity is 0 and the bob is 0,04 meter above the lowest point. So the total mechanical energy at point A is equal to 0,0196. Since this is a closed system, the total mechanical energy at point B is equal to the total mechanical energy at point A. Substitute all the known information into the formula. So we get 0,025 multiplied by velocity at B squared is equal to 0,0196. The last step is to solve for the velocity at B. Our answer is 0,885, which rounded off to 0,89 meter per second. If you try to solve this problem using an equation of motion, you get the identical answer. It is, however, incorrect, since the equations of motion can only be used for motion in a straight line and the pendulum moves in a curve. This would be an error in principle. Our next example is the conservation of mechanical energy on a roller coaster. A roller coaster can be a very scary ride, but because of the conservation of mechanical energy, you will be safe. A motor provides the cart with maximum potential energy at the top of the track. After that, total mechanical energy is conserved if there is no friction between the track and the cart. The energy interconverts between kinetic energy and gravitational potential energy. Take note that the total mechanical energy of the system stays constant all the time, but the kinetic energy is zero at the highest point and a maximum at the lowest point. The roller coaster cart cannot exceed the energy at the maximum height of the roller coaster track, so the velocity at the lowest point is controlled. Please refer to the task video for more of the roller coaster kinds of problems. There is one more application of the principle of conservation of mechanical energy, and that is the motion of an object on a slope, also known as an inclined plane. Consider a cyclist and his bicycle as he freewheels down a hill. He is moving at a velocity of 2 meters per second at the start at the top of the hill. The hill slope is 100 meters long and it is at a 30-degree angle to the horizontal. The combined mass of the cyclist and the bicycle is 80 kilograms. Determine the velocity of the cyclist at the bottom of the hill. The total mechanical energy is conserved if we ignore friction. All the energy at the top of the hill is the same as all the energy at the bottom of the hill. To solve this problem, we first need to find the vertical height of the hill, which is also the cyclist's change in height. We know that the road downhill is 100 meters and the angle of the slope is 30 degrees. We will use trigonometry to calculate the height. Sine theta is equal to opposite over hypotenuse, which means that sine of 30 degrees is equal to the height over 100. So height is equal to 100 times sine 30 degrees, which equals 50 meters. Now that we have the vertical height of the hill, we can calculate the cyclist's gravitational potential energy, which is mass times gravitational acceleration times height. Substituting the known values, we get that the gravitational potential energy is 80 times 9,8 times 50. So, the cyclist has a gravitational potential energy of 39,200 joule when at the top of the hill. But now, we have to remember that the total mechanical energy is the sum of the gravitational potential energy and the kinetic energy. And since the cyclist has a velocity of 2 meters per second at the top of the hill, we'll have to add the kinetic energy to the gravitational potential energy to find the total mechanical energy at the top of the hill. So, we will use the formula for kinetic energy to calculate the kinetic energy at the top of the hill. That kinetic energy is equal to half mass multiplied by velocity squared. Substitute the mass of 80 kilograms and the velocity at the top of the hill of 2 meters per second squared. So, the kinetic energy at the top of the hill is 160 joules. So the total mechanical energy at the top of the hill is the gravitational potential energy plus the kinetic energy. We find that this adds up to a total mechanical energy of 39,360 joules. Since no energy was lost due to friction, we know that the mechanical energy of the system is conserved. So the total mechanical energy at the bottom is equal to the total mechanical energy at the top. And the gravitational potential energy plus the kinetic energy at the bottom is equal to 39,360 joule. And at the bottom of the hill, the gravitational potential energy is 0, since the height above the reference point is 0. We substitute the values into the equation and calculate the answer. The velocity at the bottom of the hill is 31,37 meters per second, which is pretty fast. This brings us to the end of the series about energy. Make sure that you understand and practice these concepts that we dealt with, since this topic will be revisited in grade 12. Practice more of these problems in the task video. You'll also find more information on our website at www.mindset.co.za/learn. Goodbye, grade 10s.